In this short video, we will look at analyzing a simple probability distribution function. Let's look at this example question. A probability distribution function is given by f of x equal to k times e power minus lambda x for x greater than or equal to 0 and 0 otherwise. And the questions are to find k, find the mean and find the median. Okay, let's start by actually plotting this probability distribution function. How does this look like? So here's your x values and this is your f of x, the density function. So e power minus lambda x is the core here. So as you know, it's going to be a decaying function like this, going all the way to infinity asymptotically, going all the way to 0 as x approaches infinity asymptotically. And the value here is of course k e power minus 0, which is k. So this point is 0 comma k. Now what we want here is the value of k itself. So clearly the area under a probability distribution function must be 1. So we integrate this k e power minus lambda x dx. And since the distribution function doesn't have any weight outside of 0 to infinity, we don't have to bother integrating anything here. So it's 0 to infinity. So which is k times the integral of e power minus lambda x is e power minus lambda x by minus lambda. And let's apply the limits from 0 to infinity. The upper limit is e power minus lambda times infinity, which is 0, minus the lower limit is e power minus lambda times 0, which is 1. So we get k by lambda. But we know that this integral should be 1 because the area under a distribution function is 1. And therefore, you get k by lambda equal to 1, which implies k equal to lambda. Okay? For example, if lambda is 3, then the function is 3 e power minus 3x. So, on that note, let's say lambda is 3, then this point is 0 comma 3. A common confusion that students have is how can probability be more than 1? The probability is not more than 1, the distribution function is more than 1. The probability is found by finding the area for any small region. So let's say for example if this is 3 and let's say at this point the value is 2, the probability of this small region would be approximately 2 times delta x. This delta x is fairly small, and that is guaranteed to be smaller than 1 because delta x is very small quantity. Okay, that's an aside. So we found out k in terms of lambda. The next question is to find the mean. Okay, how do you go about doing it? Probably we'll do the median first since that's easier. Okay, we have done this. Let's look at the median since it's very related to the integral that we have here as well. So what is a median? A median in a continuous distribution function is a value such that, a value of x such that to the left of that there's 50% of weight and to the right of that there's 50% of the weight. Just like in discrete terms, the median would be the middle value. If there are 1, 2, 3, 4, 5, 6, 7, 8, 9, then you say the fifth one is the median. Why? Because there's equal weight on the left and the right. In continuous case, the same sort of analogy applies. The integral of the density function should be half here and half here. So all that changes is, rather than integrate it to infinity and set it to 1, the question now is, I'm going to erase off this section here. Now that we identified that k is lambda, I can replace it by lambda. And we are not setting it to 1, we are setting it to half, and we are not integrating till infinity, we are integrating till such an m that we have to find, and that m becomes the median. So if you integrate from 0 to m, let's say, if that area happens to be half, that value of m becomes the median. So let's complete this integral here. So the same thing, so integral of lambda e power minus lambda x is this. And let's apply the limits. The upper limit is m, the lower limit is 0. The lambda cancels off first of all. So the upper limit is just e power minus lambda m. And the lower limit is with a negative sign. And the lower limit is e power minus 0, which is minus 1. So it's effectively 1 minus e power minus lambda m. Okay, so let's continue here. So we want this quantity 1 minus e power minus lambda m to be half. In other words, let's bring the half here and let's reciprocate both sides. 1 by e power minus lambda m is just e power lambda m. Now let's take natural logarithm on both sides. Therefore ln of 2 equals lambda m, and the median we are seeking therefore just simply becomes ln 2 by lambda. And if you want to know approximately ln 2, which you would encounter a lot in half-life, it's approximately 0.693 or 0.7. So that is the median of this distribution. Okay, so we found k happened to be 1 by lambda. We also found the median, which happened to be 1.693 by lambda. Just a small note on dimensionality. E power lambda x, this quantity, the power here has to be dimensionless. And sure enough, it makes sense that x and lambda are of different dimensions here. Right? So if, for example, if x is of the dimension of the median, let's say we are talking about the waiting time or something, right? X becomes time and lambda becomes 1 over time, which is why 1 over lambda becomes time again. Okay, that's a small note. You don't have to worry too much about dimensional analysis here. Okay, let's move on to the next part, which is finding the mean. Okay, we are done with the median as well. Okay, how do we find the mean? Okay, let's erase this off here. What is the mean of any distribution? The mean is nothing but, it's an expectation. It's an expectation of x, right? So before we go for expectation of x, let's understand what an expectation of some function of the random variable is. So expectation of some function of a random variable is very simply integral of h of x times the probability density function. In this case, h of x is very simply just x itself, and therefore it just becomes x times f of x dx. So that's the integral we are seeking for this problem. Okay, to get some more space, let me just erase this off here. And